Okay, for this problem, we have a computer job that passes through two independent queues. The first queue has an exponential waiting time with mean alpha. So let's call that x, and that's going to have exponential distribution with parameter 1 over alpha. And the other one is also going to be exponential, and its mean is beta, which means that its parameter is 1 over beta. So we want to find the PDF for the total waiting time, the expected total waiting time, and the standard deviation for the total waiting time. I'm going to do 2 and 3 first because they're easiest. Then I'll get to the PDF for the total waiting time. And the reason they're easiest is because the expected value of x plus y is simply equal to the expected value of x plus the expected value of y. And I know full well that's just going to be alpha plus beta. So that's simple. Next, we have the variance of x plus y. Because of independence, this is equal to the variance of x plus the variance of y. All right, now what's the variance? The variance is going to be 1 over the reciprocal of the parameter, so alpha squared plus beta squared, using my formula. And so therefore, that means that the standard deviation of x plus y will just simply be the square root of alpha squared plus beta squared. Okay, so those are easy. The more complicated thing is going to be the PDF for the total waiting time. Now, for the PDF for the total waiting time, we take a look at the joint distribution of x and y. So this is part 2, that's part 3. Let's now back up to part 1. To find the PDF for the total waiting time, I remember that x is exponential, y is exponential, so everything's going to be positive. And what I need to do is take an integral that looks like this. I'm taking cuts off of this distribution. And the specific formula for the sum is going to be integral from minus infinity to infinity of the density evaluated at x times the density of y evaluated at z minus x dx. All right, now for this to work, we need to have x has to be greater than or equal to 0 because x is exponential. Also, we need to have z minus x greater than or equal to 0, which means that x is less than or equal to z. So my range of integration, x has to be between 0 and z for this to work. And my density function here is 1 over alpha e to the minus x over alpha. The density function for this one will be 1 over beta times e to the minus. Now, instead of x, I've got z minus x, so z minus x over beta dx. Then I just have the small matter of doing this computation. To make this as simple as possible, let me pull all constants out, everything that doesn't have an x in it. So 1 over alpha can come out, 1 over beta can come out. Also notice that e to the minus z over beta can come out because that does not have an x in it. So what's left is integral from 0 to z of e to the minus x over alpha times e to the plus x over beta dx. So 1 over alpha times beta, e to the minus z over beta, and this becomes integral from 0 to z of e to the x times 1 over beta minus 1 over alpha dx. Okay, now I just do the integral. So 1 over alpha times beta, e to the minus z over beta. Okay, so the integral of e to the x times this will be e to the x 1 over beta minus 1 over alpha divided by 1 over beta minus 1 over alpha. And I evaluate this between z and 0. Now if I multiply here, just in the bottom, alpha times beta over 1 minus beta, that's just going to be alpha. And alpha times beta times 1 over alpha, that's beta. So the denominator simplifies considerably. The rest, if I plug in z, I get e to the z 1 over beta minus 1 over alpha. And when I plug in x equals 0, I get e to the 0, which is simply 1. Okay, now I can do a little bit better than this. If I multiply this by e to the minus z beta here, so I have 1 over alpha minus beta. If I multiply this by e to the minus z over beta, that becomes simply e to the minus z over alpha. And if I multiply this by 1, I get minus e to the minus z over beta. And so that is the PDF for the sum of the two random variables. And this works. X is positive, y is positive, so the sum must also be positive. So z must be greater than or equal to 0 for this to work. Now, hypothetically, if you take the expected value of this and find the expected value of z squared and so on, you will match that the expected value of the sum is equal to alpha plus beta, and the standard deviation of the sum, it works out to be square root of a squared plus alpha squared plus beta squared.